discharge is constant. Now, if we think about a natural channel, then definitely for a region like India, where our rainfall is fluctuating a lot, I mean, seasonal variation of rainfall is quite high. And there, we cannot imagine of having a fixed discharge through any natural channel. So though we see that this channel is in regime condition many a time, but it is not exactly true. Of course, there we find that for the dominant discharge, this can be considered to be in regime condition. But when discharge increases, again a channel may get eroded, and again there may be deposition in the channel. And that's why for the river of India, where the rainfall is more, suppose rainfall is more in the again northeastern part of India, if we talk about where rainfall is very high, then in those areas the discharge is fluctuating a lot, and that's why the channel to have a perfect regime condition is not possible. It always keep on changing, and that's why we are getting braided channel, then channel meandering is taking place, channel, because at some point the sediment get deposited at certain point, and in other part it is getting, in another season it is getting eroded. So that sort of things keeps on going. But when we talk about man-made channel, because when we are talking about design of channel, we are basically talking about man-made channel. Then suppose man-made channel means it can be irrigation canal. If it is a irrigation canal, then of course we can think to some extent about a constant discharge. If we feel that for the irrigation will be supplying a constant discharge. But again, here also that point comes. Because if our agricultural field is in a region like India, this will require irrigation only when it is not raining or when the crop is facing water stress. So we are not always allowing the same amount of water to the canal. Because again, if it is controlled by a reservoir on upstream, we need to store water when the rain is coming, and then we need to release water when the lean period. And that's why we cannot afford to have constant discharge. But still, there can be the variation we can minimize, and we can think of having some constant discharge. And of course, if the canal that we are designing is a drainage canal of a city, then definitely this condition cannot be satisfied. But still, we need to design with some assumption in this part, with some discharge considering as the dominant discharge. Then, next point is that means for true regime condition, this must be satisfied, the first point. Then silt grade and silt charge are constant. Well, what we mean by silt grade and silt charge. Silt grade means the size and distribution of the silt size, rather. Say sometimes we call well graded silt, sometimes we call poorly graded silt or uniformly graded silt. Means poorly, if in a silt portion, if we find that all silt are of uniform size, then it is uniformly graded silt. And when it is uniformly graded silt, means all are of almost uniform size. This is not good, rather it is bad, because if we have say smaller size, bigger size, then all will get, say, smaller size particle will go inside the bigger size particle, like that. Say these are bigger size, and then these are suppose some smaller size. So the smaller size will go inside, and then the interlocking will be better. So, but if it is a poorly graded, that's why if it is a uniformly graded, all are of the same size, then there will be lot of gap in between, and that's why these are called poorly graded. So, and well graded means when there are smaller and bigger mixed different size. So like that, this is basically the gradation of the silt, we call like that. But to represent this, we need a value. So generally, the average particle size is given to use the gradation. And in this case, of course, when we talk about grade, our emphasis is to see that whether if the silt are of bigger size, then it will not be eroded easily. If they are of smaller size, it will be eroded easily. Of course, if it become very fine, then of course it is not coming under alluvial formation. Then if it become clay, that is not erodable. That is a different thing. Its adhesive property or its cohesive property is very strong, and that creates some other sort of bonding. But when we are talking about alluvial formation, then if the silt is of finer size, it will be eroded quickly. And so the average size of the particle is significant. And that's why this by silt grade, we mean that what is the size of the silt, and that can be represented as D50, means that if we use sieve analysis, and then suppose we are sieving the entire silt, and then we are finding that how much percentage of the silt is passing through the, 50% of this is finer than that say particular size, and then that we refer as, that particular size we refer as D50. That is 50% of the silt will be finer than that particular size. When 50% is finer, definitely 50% will be coarser than that. So that particular definition we use for representing the silt size. And then what is silt surge? Well, silt surge means the volume of silt that is coming into this channel. And then suppose not only the size of the particle, what is the total silt concentration, sediment concentration in the water. So sediment concentration is flowing means it can be in the suspended form, it may be moving through the bed. So how much total sediment over the bed, as we were discussing that part earlier also, that is the bed load and suspended load. So that way, what is our, say when we were discussing mobile boundary channel, I recall. So when we were discussing mobile boundary channel, then this part we were discussing uniform flow in mobile boundary channel. So in that case, we were discussing that sediment can be moving along the bed by jumping or rolling, or it can move in getting mixed up with the water. So entire things, total concentration of bed load and suspended load we call as a silt charge. So how much silt charge is coming, that is important. But the point is that in Kennedy's theory or in Lacey's theory, we are not using any parameter to take care of this silt charge. We are just considering that it will be in regime condition, that when silt charge that is flowing through the channel and the silt grade is constant. Well, then next point, this is more important, that flow occurs in an incoherent alluvium, that is cohesiveness is less, incoherent alluvial, that is it is a alluvial soil, incoherent alluvial of unlimited extent, carrying silt grade same as that of the formation. So this sentence, what it means, that for true regime condition, to have true regime condition, our channel should be of infinite extent. That means infinite extent of incoherent alluvium is there, and through that our channel is moving, and then it is carrying silt grade same as that of the formation. So in the bed through which the channel is going, the suppose through a particular alluvium the channel is moving, so the sediment size of the alluvium, silt size of that alluvium, we will be getting some value. If we take some sample and if we see what is the D50 of that we are getting there. And then what sediment it is coming from upstream, that is coming from far upstream, and that is coming as silt charge. And in that silt charge, the value what we are getting, the dimension or D50 of that what we are getting, there, okay, D50 may not be the index, we can use some other index also in case, but whatever index we use, the size of or the grade of silt charge that is coming from the upstream and the grade of silt charge that is remaining in the bed, this must be same, and that entire alluvium should be of infinite extent, and then only we can have true regime condition. Now when we go into these 3 points and when we think about these 3 points, then one point is very clear, that when we are talking about application of Lacey's theory, then we know that true regime condition, if it is to be achieved, then it is very difficult in the field, and that way there will be definitely some error in the design or limitation of the design. Well, then some other important point when we are talking about artificial channel, that artificial channel, there are 2 stages of regime. Well, we are now till this point, we are talking about regime condition. Then we are talking about true regime condition. What are the conditions that we should have? But in artificial channel, when we are making an artificial channel, then there are two stages of regime. So this is called two stages of regime. One is called initial regime and the other is called final regime. And of course, some more points are there that we need to know, but still, as a beginner, we should know that what we mean by initial regime when only depth and slope has undergone adjustment. So initially, when water will be flowing through a channel, then the depth of the channel and the width of the channel, finally the width will also get adjusted, but initially the depth of the channel will be adjusted. Means if the velocity is high, it will be scouring in the depth wise direction, so depth will be adjusted and the slope of the bed will also be adjusted. Well, so initially the depth and slope get adjusted, and when these two are getting adjusted and we are getting more or less a stable channel for some intermediate period, and this is called initial regime condition. And then of course after some time it will start eroding from the side, and then its width will start increasing, or if it may get decreased also if deposition start, means width will start adjusting. So when both when this three parameter, that is depth, slope and width, gets finally adjusted, then this is called final regime condition. So once we get initial regime, then we call this as a final regime condition when width has also undergone adjustment. And in the entire process, the side slope is also getting adjusted. Side slope is also getting adjusted. When we are talking about a regime condition, we say that side slope will have its own value based on the erosion and deposition. So that way, we are not providing a side slope directly here. That we will assume that for the regime channel, this is the side slope. Of course, in Kennedy's theory, we were not talking about the side slope, and based on the sediment characteristic, we can have some side slope there. But here, we are saying that in Lacey's theory, side slope will get adjusted. In fact, he suggested some value for the side slope, or from observation, it can be taken that side slope can be taken as 0.5:1. That is for one depth, 0.5 width. So that way, the side slope can be considered. But one more important point that I am putting in red here is, you can concentrate on the slide, that it is not necessary that to reach the final regime, the channel will have to pass through initial regime. So the channel need not pass through initial regime to reach the final regime in all cases. Normally, it goes first to initial regime, then it achieves its final regime. But sometimes, without passing through the initial regime, it can reach its final regime. For example, suppose final regime width of the channel should be, say, 5 meter, for example, and we have made a 6 meter wide channel, and then the flow is flowing through that. So what will happen? The depth wise it is adjusting, and then width is also getting deposited. Channel sediment that is carried by the channel may be depositing on the side because width is larger, and that way by depositing finally it is coming to the width of 5 meter, which should be in the regime condition, and that way we may get a regime channel without passing through the initial adjustment of only bed and slope. So that way this is not the necessary criteria. And then more importantly, Lacey's theory, what he studied, and based on his study, what are the formula he has given, those are applicable for final regime condition. So once we are designing a channel, we should know that this channel we are basically designing considering that this is the final regime size. And so those formula will be giving us this value. Well, then he gave series of formula. Initially, of course, he gave 4 formula. These are the 4 formula that were given by Lacy. First is that this is not exactly a formula, that it was found, or it was rather observed in many cases, that side slope, it can be considered as 0.5:1 for when we are designing by Lacy's formula. The side slope we can put like that. And of course, the next formula, or this 4 formula what he gave, is that unlike Kennedy's formula, where the silt factor was not given at all importance, later on only they introduced a term called M, the critical velocity ratio, which was used to take care about the silt factor. But unlike that, Lacy first gave the formula for silt factor. Silt factor F, he gave this formula as 1.76 root over MR, where this MR, that is, which is basically representing the particle size, and that MR is considered as D50. That MR is considered as D50. So, for the design of Lacy's channel or Lacy's theory, application of Lacy's theory, if we go to the field, first we should collect the sample through which the channel will be made. Then after collecting the sample, we should carry out sieve analysis. And then after carrying this sieve analysis, then we should see that the size of the sieve through which 50% finer we are getting, that we should consider as the D50. And that D50 value we should put here, and then that we should consider as a representative value of silt factor F. Otherwise, silt will be of different size definitely, and we need a definite value. So that definite value we are getting by this approach. Well, then we should calculate the mean velocity. And then he gave some relationship between, in fact, he gave 4 relationships. One relationship is between the mean velocity V and this R. R is nothing but hydraulic radius. And that is what this A by P. R is equal to A by P. Well, we know that in Manning's formula, or in our uniform flow formula also, we relate this velocity to the hydraulic radius R, and then we take care of the slope. But here, this is the velocity which we try to achieve, and then this velocity is equal to, is given as 2 by 5, rather root over 2 by 5 FR. Again, silt factor is playing a role here. And in fact, in all those formula, in most of the formula that he has given, the silt factor has a vital role. So the determination of the silt factor is very important. Well, and then the V, we can have 2 by 5 F into R to the power half. So that relation he gave. Then he gave another relation. So here